Welcome to Team 10's video for the portable CO2 monitor. From left to right, we are Nolan, Miheer, Owen, Matthew, and Dr. Chap. There are currently no standardized quantitative methods for monitoring a patient's post-anesthesia carbon dioxide levels during patient transport, leaving hospital staff reliant on subjective assessments that carry significant risk of complications. Okay, that's good. This is what our CO2 monitor looks like from the front. When you press the button on the very right, it switches on. When you press the start button on the touch screen, that's when it starts recording the patient's breathing. The capnographic waveforms that you see are when the patient breathes in and breathes out, and you can adjust the thresholds for alarms by pressing the low button, pressing plus or minus depending on whether you want the millimeters of mercury to go up or down, and pressing the button simply again in order to set that as the value. High cannot go below the low threshold, and low cannot go above the high threshold. On the graphical user interface, we have several other indicators as well, using charging, humidity, temperature, and flow, where it lets you know if there's any issues with any of those three, whether you need to charge it, or if there's condensation issues, temperature issues, or if flow is blocked. The decibel volume was reduced for this video, but these alarms can be muted with the mute button, and they alert healthcare professionals to the breathing levels of the patient. On the top of it, you can see a little battery drawer where you can open up the slot and see the actual connection point where you can charge the battery if it goes low. And on the right, you can see the toggle latch, which you can open in case you need to access the internal parts of the device, which look like this. It features the PCB, all the electronic connections, and the pneumatic workflow, which begins from the lure lock connector that goes to the build filter that stops condensation from entering our line, and then air is sucked in through the diaphragm pump that we have, which then goes to the RH and temp sensor that enables us to tell if there's condensation in the line, as seen by that T over there. Behind the pump, which you can pull back to view. After this relative humidity and temperature sensor, we are then going to the pressure sensor, the absolute pressure sensor, so we can do pressure compensation and enable more accurate readings of CO2 accordingly to higher pressure in the line or different altitude levels. Then we go to the actual CO2 sensor, which works through non-dispersive IR sensing, and finally the flow sensor, which enables us to tell if the sample line is blocked. And this wire that I just ran my hands through goes to the screen and enables us to display the capnographic waveforms, all the alarms, and have touchscreen enabled for the users to be able to use. If you switch the device back on by just simply pressing the switch and closing the toggle latch, it's good as new and ready to keep going. Now taking a look at the electronic components outside of the pneumatic workflow, we have the ESP32 connected to the PCB, the battery, and the protoboard that enabled us to actually interface the flow sensor, which is a major challenge for us for a long time. On the back of the 3 current casing, we have a clamp that opens up completely, makes it much easier to put onto the intravenous or IV pole. The mounting of which is shown over here enables us to use the device during transport of the patient into the ICU or PACU. Thank you so much to our sponsors, Dr. Jeffrey Chapman, Dr. Kyle Norton, and Sean Chapman, who is a current MD PhD student at UCSD, for the opportunity. The MA 156 instructional team, which includes Professor Polikakos, Professor Gazinejad, our TA Alex Potts, and the ever helpful Greg Hainline, as well as the rest of my team, which comprised Team 10 Portable CO2 Monitor, which we titled CO2Go. Thank you.